Hello and very good afternoon, everyone. I'm Mohammad Tehrani, and I would like to welcome you all in the third session of the first edition of the Water-Based Wednesdays webinars. This is a sharing time which is planned to be held a couple of times during the year, sharing the and water-relevant issues. For those sessions where the speaker will attend in person, the webinar will be conducted in hybrid mode, and unfortunately, this time also is not the case. Each session will be featured dynamically with the presentations lasting approximately 30 to 40 minutes, followed by an interactive 20 minutes, about 20 minutes of question and answer session. Before we dive into the talk, a quick reminder to stay engaged, please, and feel free to ask questions using the chat box, and we will address them in the dedicated Q&A session. At the end, you could turn on your mic and the camera and ask it directly to our speaker. Today is no exception, and this is the third session of the 2024 series. We have a distinguished speaker who will share his expertise on the numerical modeling of hydrodynamics and water quality. Whether you are a pioneer, senior, professional, or just a young beginner in this area, get ready for an engaging, informative session. And without further ado, let me introduce our esteemed speaker for today, Dr. Syed Abbas Saadabad, who is currently a senior postdoctoral researcher at the Institut National de la Recherche Scientifique INRS, Quebec, Canada, working on the water quality modeling in St. Charles Lake, a drinking water reservoir in Quebec. He received his PhD in Environmental and Infrastructure Engineering in 2017 from the Politecnico di Milano, Milan, Italy. His work at the Polimi mainly was to introduce a novel conceptual framework to define and study the Lagrangian and Eulerian descriptor for the bed-load sediment transport in rivers. He then joined Toosi University of Technology, Tehran Polytechnic in Iran in 2018 as a postdoctoral research fellow, and has been involved in analysis of 2019 floods in Iran, taking into account the management of the risk through the multi-hazard approach and to guarantee the climatic strategy and operation. He also created the Einstein's equation for the bed load sediment transport and modified a new version of this equation with better predictability of the load fluxes. His current project at INRS aims to conduct a comprehensive 3D numerical simulation to assess current water quality condition in St. Charles Lake, while also projecting further or future scenarios. The simulation will provide valuable insight into the lake's water quality dynamic, enabling better management and conservation efforts. Without any further words, Syed Abbas, thank you for accepting to be with us today. And the floor is yours. I told everybody good afternoon. I must say to you very early morning, good morning, and the floor is yours.
All right, good. So hello, everybody, and welcome to this presentation. It's pretty early in the morning in Canada, and I'm currently at my apartment, and there is trucks passing by, so you might hear some noises, but I closed the window so that less disturbance is engaged. Okay, Dr. Mirza, I cannot share my screen. I think you have to let me
pass you the visitor as a presenter. I just have to read efficiently, I hope. Yeah, I think now you have the access to share your screen.
That right now, then that's fine. Yeah. All right. So I'm gonna share my screen, and hopefully my presentation is there. Okay. You must be able to see the first page of the presentation now, right?
Yes, we see it perfectly. Please.
All right. Can I begin?
Of course.
Hello?
Go ahead, please.
All right, okay. So good afternoon to you, all the fellows in Iran. And I saw some other name that welcome her as well from anywhere in the world. So today I'm gonna talk about 35 to 40 minutes about the importance of 3D water quality modeling, and especially in a case study in the province of Quebec, Canada. So this project has been funded by Government of Canada and as well as MITEC's scholarship. Basically, two major persons involved in the project are myself and Professor Alan Rosso, who's been a friend and a real advisor to this project. So you told me about my background, and Professor Rosso got his master's degree in agricultural water resources in Laval University in Canada, and then proceeded to master's degree in University of Guelph, and he got his PhD at Cornell University, United States. He is a pretty renowned scientist in the fields of hydrology and drainage engineering. So without further ado, I'll proceed. So today I'm going to talk about a specific case. It's Lake St. Charles. It is one of the most critical and strategic lakes in province of Quebec. It supplies drinking water to nearly 300,000 people. So is everybody hearing me?
Yes, we hear you.
All right.
No
Okay,
worries.
good. All right, okay. So in this project, we try to use a 3D numerical model to investigate the hydrodynamics and water quality of this lake. So I give you a little background about the lake. As you can see, I don't know if you see my mouse. However, on the right, this is the watershed of the lake, and this is the map of Canada. And here is Quebec province, and this is the location of the lake. What you can see is the lake is actually majorly fed by the Holmes River watershed, and this is the bathymetric data of the lake. You can see that the lake has a deep and a shallow basin. Other physical and meteorological characteristics of the lake are summarized in this table. We can see the surface area is around 4.5 square kilometers. The watershed area is about 170 kilometers squared. And the annual retention time is 37 days only, which then characterizes this lake as a fluvial entity. So I'm going to give you a little background about the algal blooms. So in the last 50 years, due to the industrialization, the algal bloom in Canada and specifically in Quebec, and that's the case typically for shallow and eutrophic bays. And the land use change and climate warming have been identified as the main causes of algal bloom in water bodies. And several studies have indicated the growing evidence of urbanization and domestic wastewater discharge into the lake, which in turn results in constant degradation of water quality and rising major concerns for stakeholders, city managers, and whoever benefit from the lake. So there are two examples of algal bloom in the lake. They're around the shore, so you can see what the algae looks like. However, not in general algae is bad, but when you have abundance of algae, then you might have some toxic algae, which then can damage some organs in the body, and it's pretty poisonous. So I'll explain the methodology that we use for this lake. So what you can see here is that we built up, simulated, and calibrated a model based on three-dimensional environmental fluid dynamic code. It's a pretty famous code. However, for input to the model, we need some meteorological, hydrological, and water quality data as model inputs, and the model will then simulate the whole processes within the entire basin. Here is an example of the software environment. So before we start simulations, we looked at the data that we already had. So basically, if you look at the lake here, you can see that the lake is surrounded by almost 40 monitoring stations across the lake, where you can see. So we merged these 40 stations into 8 tributaries for the model. And what you can see on this map is that this is the location of tributaries and the name of the tributaries. So all the flow and nutrients are coming from these 8 tributaries. And in addition, we have 5 monitoring stations inside the lake in order to compare the observation versus simulations. In other words, calibrating the model. So the hydrological data for this case study comes from a semi-distributed hydrological model. It's called Hydrodynamics. It has been developed by Professor Rosso and his team in our group at the Institute of National Research, Quebec. So what you can see here, there are the simulations of the flow from 1969 to the end of 2022. What you can see here is that the majority of the water, significant portion of it, 85% of it, is coming from the Holmes River, which is located in the north of the Quebec, as well as the remaining 15% of the water is coming from different watersheds. So, and if you look at the flow in time or hydrograph, you can see that the values of the flow for the Holmes River is some order of magnitudes higher than all other tributaries, indicating that that's the main driver of the lake. So for meteorological data, we needed solar radiation, we needed ambient temperature, we needed relative humidity, cloud cover, and atmospheric pressure and all that. So for those data, we partially used the Environmental Climate Change Canada station near the airport of Quebec City. And in addition, we use Meteor Blue, which is a Swiss, it's a Swiss climate model. So you can extract the meteorological data from almost everywhere on planet Earth from a Meteor Blue. This is a very good Swiss-made climate model. So for what you can see here, so as an input to the lake, we need the values of water quality as well as the water temperature. So as I mentioned before here, there are 40 stations around the lake, and the data are collected by an organization called AGIGRO, which is responsible for taking care of the sampling and the total health of the lake. So we wanted to run the model for 8 years from 2015 up to 2022. But what you can see is that, for example, the dissolved oxygen values for this station, the data are sporadic, and they're typically collected from April until November. And for the rest of the year, we do not have any data. So in order to fill the gaps in this time series, we use generalized additive models as well as random forest model in some other machine learning methods to fill the gaps in the observation. Here's an example. What you can see here is for these 8 years of simulations, we only had data which are presented by red dots here, but the blue ones are reconstructed time series, daily time series using GAMS and random forest. Okay. So the next thing before we started simulation, while we collected the data, we were looking at the concentration of total phosphorus and total nitrogen, major drivers of algae. What you can see here in terms of concentration, which is a kilogram per liter per day, the tributary 216 has the highest values of concentration coming to the lake. However, this is not important. What is important is the total amount of load that comes to the lake. And that is basically a product of concentration times flow. So when you look at the concentration times flow for the total nitrogen and total phosphorus per kilogram per day, what you can see is that the Holmes River, which has 80% of the water coming to the lake, has also the highest amount of loads coming to the lake. So if you look at the log scale on the y-axis, you can simply see that the values are within 2 order of magnitudes higher compared to all the other tributaries. And here you can see the drainage area of different tributaries. And what you can see here is that the Holmes River is around 40,000 hectares of drainage area. So the next step was we look at the data collected by a geo, and then we look at the ratio of total nitrogen over total phosphorus. And from 2015, what you can simply see, and that is also true for all the preceding years, is that on average, the total nitrogen ratio, the ratio of total nitrogen or total phosphorus is above 20, which actually indicates that the lake is phosphorus limited, meaning that phosphorus plays a more important role in the formation of algae than nitrogen. So the next step was to look at the total loads coming in versus total loads going out of the lake. So what you can see is the time series of the total loads coming to the lake from the Holmes River and all of the tributaries from 2015 all the way to the end of 2022. What you can see here is that in general, the peaks are associated with spring, when the snow melts and the water runs into the lake. And again, what you can see that the Holmes River is the most significant contributor to the lake. And here is the amount of phosphorus flushing out of the lake throughout the outlet. And here is the difference between what comes in minus what goes out, which actually indicates when it's positive, the lake is maintaining the nutrients, and when it's negative, the lake is flushing out the nutrients. So that the same story is also true for total nitrogen. And so you can see the same trend here. I'm going to pause for a little while and see if everybody is hearing me, if the presentation is going smoothly. Is everything okay?
Yes, Abdulson, it goes well, and we hear you well, and the presentation is
All right,
going
okay.
on.
So I'm gonna make sure that we're on the same page. All right.
Yeah.
So I'm gonna continue. Then we look at the seasonal analysis of total phosphorus and total nitrogen, again per kilogram per day as the loads. And what you can see here on this figure is the minimum, the maximum, the 10%, 90%, and the median. What you can see here is that generally in spring, the values are higher. And that's basically because of the snow melting event. And what you can see here, that spring is also associated with relatively short retention time. However, when you go to summer and winter, you can see that the retention time is longer, meaning that the water stays longer in the lake. And as such, the total loads of phosphorus and nitrogen are less. So here is the year-to-year analysis of total phosphorus versus nitrogen. It's per season, per year. What you can see here is that, again, the peaks are associated with spring, and that's it. So when you look at the total loads of phosphorus and in terms of kilogram per hectare and in terms of tons, where you can see from 2015 to 2022, the total amount of phosphorus per kilogram per hectare from different tributaries is given here. And in terms of tons is given here. So what you can see here is that in terms of tons, the Tehrani River is releasing around 2.4 tons of phosphorus into the lake, whereas the total amount is 2.8. So meaning that, again, more than 85%, around 90% of the loads are coming from the Tehrani River. Then again, we look at the total loads of nitrogen coming to the lake in terms of kilogram per hectare, as well as in terms of tons from 2015 to 2022, and from different tributaries, again highlighting the important role of the Tehrani River with 68.6 tons of nitrogen releasing to the lake. All right, so now we looked at the data for different tributaries as input to the model. Now we're going to simulate the lake, because so far we just talked about the tributary values. We didn't talk about what's inside the lake. So now it's the job of the model to simulate the lake. So here I give you a little bit information about the model. The model is called Environmental Fluid Dynamic Codes. It was initially developed by Hamrick in 1992 and it's been constantly updated by Environmental Protection Agency in the United States ever since. I'm not going into the detailed equation of the model, but just for your information, the mass balance equation is as follows, and the production of algae biomass is described as this equation within the model. For details, you can always go to the user manual or on the website of the Environmental Fluid Dynamics codes for the codes and the equations inside the model. All right, we start with the simulation of temperature. So here I show some results from 2015 to 2017. As I said, there are 5 monitoring stations in the lake. We pick up 2 stations to show the results. And this is the computational grid. You can see that we have results for every grid. But I'm going to show you the results only for station C05, which is in the shallow basin, and station C08, which is in the a deep basin and to compare the results for the two basins. So what you can see here is that for shallow basin, the temperature is, as you can see during the winter, the temperature is pretty much uniform. And then when it comes to summer, the temperature rises. However, it's throughout the entire water column, which is 4 meter deep. The value does not vary significantly, and so does the values of dissolved oxygen are around, usually they are higher in summers and springs, and they're around 10 to 12 milligram per liter. However, when we look at the deep basin, we can see a stratification happening in the lake, meaning that starting in late spring and summer, the lake becomes stratified. For those who do not know what stratification is basically when we have deep water in lakes, and when the water becomes warmer, the density of the water the density of cold water becomes higher, and as such the cold water goes down, recirculating the pattern of the mixing with the higher temperature on top and the cold temperature on the bottom. So the same story is also true for dissolved oxygen. You can see the values of dissolved oxygen reduce as we go throughout the depth. The higher values are in the first, let's say, 4 meters of the 4 meters from the surface of the lake. As far as you go down, the values of temperature decrease, and also the dissolved oxygen decreases. Temperature and dissolved oxygens are one of the two crucial parameters for the health of water body. So then in this table, I'll show you an example of difference between modeled and observed data for the five different stations, namely C01, C03, C04, C05, and C08, where you can see here the observed average data and the model average data are pretty close. And we look at the root mean square error and also relative root mean square error. So what you can see here is all the values are below 20%. However, in water quality modeling, a value of plus minus 50% is acceptable for the simulation results. So what you can see here is that our simulation is, our model is well calibrated and simulation results are satisfactory. And also the same thing with the dissolved oxygen, where you can see the difference between the model, the average model and the average observed are pretty low, with an RMSE and RMSE measured again below 20%, which is adopted for the simulation of dissolved oxygen. Okay. Once we calibrated the hydrodynamic model and we looked at the temperature and dissolved oxygen, the next step was to basically look at the water quality of the lake. So here I'm going to show you the values again for the two stations in the shallow and in the deep basin. I start with the shallow basin. What you can see here is the observation in this observed line is in the dashed lines, and simulations are in the straight line of total chlorophyll A in terms of micrograms per liter. What you can see here is that the values are typically around between 4 to 5, 6, 7 milligrams per liter for the shallow basin. However, if we go to the deep basin, what you can see again, this is the observed, this is the simulated values. We can see that the model simulated the model simulated values as well as the observed values are pretty much higher on the top surface of the lake, sometimes in the mid lake, and so the values are pretty much higher than before. So again, we looked at the statistical indicators, including root mean square error as well as relative root mean square errors, where you can see that the values are again below 50% and 100%, which is the acceptable range of the model. Okay, so here I'm going to show you the synthesis of 8 years of simulation for the deep basing. Where you can see here is that this is the shaded areas are the minimum and maximum values of any parameter measured in this station throughout the depth. And here, for example, this is associated with phosphorus, and the green is associated with chlorophyll A, and the blue is associated with temperature, and the red is associated with nitrogen. So what you can see here, as we approach late spring and early summer, the water temperature starts to rise. If you look at the blue line. So by the way, the thick lines are the average values. So what you can see is that once the temperature rises, the concentration of tall phosphorus, the concentration of tall chlorophyll A also starts increasing. So there is one increase in spring, in late spring and early summer, and another increase in early autumn. So what you can see here is that this blue dash line is the threshold of eutrophic status, meaning that if the value is above 7.3 microgram per liter, then this is an alarm, because the lake might be eutrophic, and the eutrophic status is dangerous for the fish and living creatures in the lake, as well as human body. So what you can see here is that when the temperature increases and the total concentration of chlorophyll A increases, the phosphorus starts to decrease, because the algae consumes the phosphorus for production. And again, when the algal bloom starts to diminish, the phosphorus value starts to increase. But what's interesting here is that you can see that there's not a significant variation in nitrogen values. Again, indicating that phosphorus is the main consumer, is the main parameter consumed by algae, while there is abundance of nitrogen in the lake. So that's the phosphorus that basically drives the formation of algae. And here we look at the simulated surface chlorophyll A. Here is the wind rows. What you can see is that the majority of the winds are coming from southwest as well as northeast. What you can see here is, so I have captured 3 figures indicating May 17, June 7th, and October 20. What you can see is that this is the P color indicating the concentration of chlorophyll A. What you can see is that initially the algal bloom starts in the shallow basing in the bottom of the lake, and what I mean by bottom is actually in the downstream of the lake. So in the downstream of the lake, the tall phytoplankton starts forming, and then with wind and temperature rise in deep basing, this pattern moves towards the middle and the deep basin of the lake. So to cut the story short, it actually initiates in the shallow basin downstream and then moves to the center and northern part of the lake. And here is, if you look at the cross section, if you look at this red line, we slice the model from north to south, and here is the simulation of the temperature as well as the algae. These arrows actually indicates the flow pattern. What you can see here is the outlet of the lake, which is a spillway, and there is some circulation of the flow here. So again, for those 3 days, starting with May 17, you can see again that the values are higher in the values of tall chlorophyll A are higher, and starting in the shallow basin with higher temperature values. And then we move to June 7th, then the dip part of the lake starts to become warmer, and the concentration of tall chlorophyll A increases here, as well as the temperature. And what you can see is that just when the lake is totally stratified, when all the concentrations are in the dip basin, the high concentrations are in the dip basin with the high temperature. So moving then, I'm going to show you quickly an animation. I hope that Mohammad is down. So this is the tall phytoplankton, surface phytoplankton. As you can see, when the model starts in January, there's not much happening because the water is cold and algae do not form in cold weather. However, if I scroll down a little bit, when we start in late spring, where you can see that when in late spring and early summers, the algal bloom is formed and then is moved towards the shallow basin. So this is the total. So you can see the concentrations are above 7, sometimes 7.4, which is the limit of eutrophic status. Okay, moving to the next slide, I'm going to show you something like the same story for this slice of the lake. When you can look at the longitudinal cross section, we can see again here, not much is happening in winter, and the value, the total phytoplankton concentration is pretty low and harmless. And then starting in, let's move a little bit, in late spring and summer, the concentration starts to increase. And it starts to increase from, again, starting from the shallow basin, moving all the way to the deep basin. So we're not going to show you all the animation. It takes a lot of time. So then we looked at the algal pattern, and we look at the cyanobacteria, green algae, and diatoms. They are the 3 major forms of phytoplankton. What we can see is that initially in spring, in late spring and early summer, the values of diatoms are the dominant values. And this is, again, this is the blue dash line is the limit for eutrophic status. Any values between blue and red are mesotrophic, and any values below the lake is oligotrophic. And so what we can see here is that starting spring, the concentration of diatoms increase, and diatoms are the dominant group of algae. And as we approach summer, the values decrease, and that's when cyanobacteria start to grow, and they get a peak in summer, and they also continue until late fall. And again, this pattern repeats for the 8 year of simulation. So what we basically can conclude is that the total concentration of chlorophyll A, there are instances where it is above the eutrophic status, but in general, mainly it is within the mesotrophic status, bounded between red and blue dash lines. All right, so I'm gonna summarize the key findings. Is The model we built upon hydrodynamic, temperature, dissolved oxygen, and water quality was calibrated successfully and could simulate the result, the parameters. The results were within the satisfactory agreement with the observed parameters. These findings were consistent with the finding of Ronald and others' observation, basically indicating that the algal distribution pattern starts in nearshore areas and then transitions towards deeper basins. And the lake central simulations consistently exhibit mesotrophic conditions, occasionally moving to eutrophic status for a short duration. From late spring to midsummer, diatoms are the dominant groups of algae. After that, cyanobacteria become the most abundant, and they will remain there until mid-fall. So these seasonal patterns were again consistent with the findings of several studies of the lake. And it's also important to note that in general, what drives algae in this lake is the fluvial nature of the lake with short retention times, the hydrology, and the nutrients, and basically the temperature. Okay, finally we can conclude with a certain degree of confidence that nitrogen is not the driving factor. Basically, what is the driving factor is phosphorus, and the lake algae formation is mainly driven by phosphorus. Okay, thank you for your attention. I think it's now 47, it's around 35 to 40 minutes I spoke. And please remember that the next event is going to be held on October 16th by another speaker. Thank you very much.
Thank you so much, Abbasjan. Thank you so much. I appreciate your very nice presentation and also very nice timing. You were quiet.
No, I was within it.
Perfect. Perfect. So now it's time for having the question from the audience side, and let me see if we have already some of them or not. Okay, I have received something. Oh, okay, thank you so much for your presentation. Okay, perhaps just curiosity and also the ice breaking. I can start with that. You mentioned about the Swiss, let's say, platform or model at the beginning for the weather. Could you please talk a little bit about that? And also, I'm curious that what was the reason for choosing that to be used? If I'm right, something like this.
Basically, if you Google Meteo Blue, you can see it's a climate model that models the meteorological condition of the entire planet Earth based on observation and simulations. And this model, the choice of this model was because it gives us the hourly time series of different meteorological data, such as solar radiation, temperature, precipitation, etc. And the more refined time series you have, the better simulation you will have for the lake. So the choice of this model was basically justified by the fact that this model is pretty much refined in terms of time series of different meteorological data. I think you can open up the microphone to audience if they have any question or no.
I think it has to be done for all now. Okay, I think that there are some ones who are typing, and please feel free to raise your hand or just turn on your mics if you would like to questions directly. And by the way, thank you for your answer, Abbas.
No problem. Always, yeah. What are the units on the figure on slide 35?
Yeah, and we have the question from Stephanie Titz. First of all, welcome, Stephanie,
okay.
and thank you. Yeah,
I'll go with
Abbas, go ahead,
Stephanie
please.
and just go back to the. I have to see if my presentation. Can you see my presentation now?
Yes, we can.
All right. Okay. Here. Okay, the units. Yeah, I forgot to put the units here. So the temperature is in degrees of Celsius, and the concentration of total chlorophyll A in green is in micrograms per liter, and the phosphorus is in milligram per liter, and the nitrogen is also. Sorry, the phosphorus is also in microgram per liter. The nitrogen, which is the red one, is in milligram per liter. Could I answer your question? Or? I'm yet to receive any. Okay.
I think Stephanie is typing. Okay.
Right.
She's just asking that those the same units that you use throughout the presentation?
Yes.
Are those?
Yes. Yes.
Okay, thank you, Abbas, for addressing this question, which was the essential one from Stephanie. Also, Stephanie, thank you so much for asking this question. Any other question, or perhaps from Stephanie anymore, or from the other audiences, any other question or comments?
So, are we waiting for any questions?
Yeah, just waiting to see if there will be some question or comment being arised, or okay, perhaps I can ask a question meanwhile, that what the dominant type of the algae that you consider for your modeling? Was there any, or perhaps I miss it, perhaps you mentioned it, or just I miss it?
Yeah, it's diatoms are dominant in spring and early summer, and then the cyanobacteria take place in mid-summer until late fall.
And
in the lake.
Is it linked with the pattern of the behavior, or I mean, does it have?
Yeah,
any
it's
effects?
exactly, the model successfully simulated this pattern based on previous studies and observation in the lake. So This is typically what happens. This is very important because then this water comes out of the lake through River St. Charles, and then goes all the way to drinking water treatment plant, and for drinking water treatment plant for supplying the drinking water to Quebec City. So it's crucial to make sure about the quality of water out of the bat, and then right out of the bat, and then transferring the water into the drinking treatment plant So it's kind of crucial to know what's happening in the lake. And there are several summer houses located by the lake. It's a very beautiful lake. You can kayak, you can have a little boat, you can swim in the lake, you can fish in the lake. So it has recreational purposes, and the lake is surrounded by more than I don't know really the number. So there's a lot of summer houses surrounding the lake. So, and a lot of people who have summer houses there, they were complaining about the green algae and also any type of algae appearing in front of their shore, and they were not happy with that. So they wanted a cleaner water, and they paid the municipality of Quebec to some money to resolve this issue.
Yeah, man. Perfect. And meanwhile, actually, we didn't receive any more comments or questions, if I'm not mistaken. Yeah, perhaps continue with the essential, perhaps a little bit crucial one. That are you confident that it needs to be really 3D numerical modeling, or it could be like 1D or any?
Well, you could always go for 1D, but then if you go for 1D water quality, then you cannot slice the lake into different layers.
Yeah.
And then it would be a lot easier to use a 1D model because they're open source codes and they're freely available. And this model is pretty costly. We paid around $7,000 US for using this model, the license of this model only for 2 years. We paid around $7,000. And it would be always cheaper to use 1D. But if you use 1D, you can never look at the stratification and how the different values change throughout the depth. So you could either go with the SQL WQ or EFDC. So we decided to go with EFDC because it's a very, very good model. It's user friendly. It's a good one.
And sorry for taking that much questions, but perhaps I will have the other one as well. That normally I'm thinking that okay, we have the good numerical modeling and good input and output results, and then the next question is, what do you think if we could or if you would like to utilize them for the lakes that we have in Iran?
Yeah, well, of course, we can use this model for the lakes in Iran. I would be very happy to be involved in any project in Iran. Maybe I could try. Well, I'm traveling to Iran next month, and
perfect.
I could be linked to some authorities in Iran in order to use the model. But at the end of the day, it's for using this model, it's also important that we have good quality input data, meaning that we know the meteorological data for the simulation period. We know that flow data are accurate. Here we have a hydrological model to simulate the flow. Of course, I'm pretty confident that there are monitoring stations across different lakes, important lakes in Iran. I was thinking to apply this model to Urumia Lake in Iran, but then again, because this model is developed by Environmental Protection Agency in the US, I don't know if they will grant us a license to be used in Iran due to all these stupid sanctions and all that. But there are other open source models. There is it's a 2D model. I know a lady in Iran who used this model for her PhD thesis. I do not remember her name. She was doing a PhD in water resources engineering at Toosi University. She used another model, but that one is 2D model for her thesis.
Okay.
And but at the end of the day, I can contact Environmental Protection Agency and see if they allow us, because I don't know if this lies within the sanctions or not, because it's academic purposes and it's nothing to do with the nuclear things and all that. So I don't know if we can use this model in Iran. I don't know.
Good. Thank you so much for addressing my question and also the other questions. So I think I don't have any more questions or comments. Just telling that me. Yes, and also Saleh. So meanwhile, I will take this opportunity to. Yeah, go ahead, please.
And complex significant special variation in depth is the model super, and of course, does the government also allow you to use it? This is the question to ask the Iranian government, not me. But and this, yeah, in response to Shiva, many lakes are relatively large and complex with significant spatial variation in depth and vein patterns. Is this model suitable for it? Yeah, it's a very good model. It's been widely used across the globe, and from China, from Europe, from I think in Europe they use Mike Orban and Delft 3D more often, but in North America we use this model more often than others. So I would be very happy to apply this model at some lakes in Iran and see the conditions of the lakes. But I'm pretty also sure that there are people who do water quality modeling in Iran, and they're experts in water quality, and I'm pretty sure about that. So I see no reason not to apply the model.
Good. Thank you so much, Shiva and Saleh, for asking this question. I'm so Abbas for addressing. If there are any more questions or comments, or you would like to ask them directly, please turn on your mic also. Meanwhile, I would like to ask you to, for being ready, because at the end of the session, we will make some group photos. So being ready, you can turn on your camera if you would like to make this group photo. And also, I would like to add that the recording of the session will be released in a few days. So for those who would like to review the presentation or miss some parts to be reviewed, or for with their friends or something like this, it will be let's say via the LinkedIn accounts and the website. It will be released on the YouTube and also Upper, so you will have the proper access to that. And the next presentation will be on October 16, where the Farhad Bahmanpouri from Italy will share his experiences and insights about his project with us. So please reserve the date on your calendar for attending that session as well. I think we do not have any more questions or comments. Yeah.
I think so too. Yeah.
Yeah. Maybe, we are almost with the time. We wrap up the webinar. So I ask those attendees who would like to make the group photo to turn on their camera, please. We will make a photo and then we will wrap.
Maybe they're lying on the bed with the laptops on the laps.
Well, that's also a possibility, but yeah.
But
We
then
will
again,
see. We will see. We have some attendees from the Lausanne and the Torino, I see. Perhaps they're at the office or something. Also in Iran, perhaps.
Did you tell Ricardo about it?
Okay. Sorry?
All right. Dr. Ostad Mirza, did you talk to Ricardo about it?
Yes, I sent the flyer yesterday also to Ricardo. I'm not sure that he was busy at this time to attend or not, but
all right, okay.
Yeah,
right,
he got informed. Yeah. Okay, now guys that we received there. Okay. Perhaps it's good if you go to the first slide of your presentation, so we will take the group photo with that. I think that would be good.
All right. Is it okay?
I think there's some delay with that.
Can you see the front page? Or you
So
what do you see? Do you see the first page? No, not yet. I don't know what's happening, but I'm on the. Let me reshare my screen again. Stop sharing.
I think I have.
All right. Okay. So.
Can you hear me now? I'm not sure.
Yeah, you're back.
The connection
I
is
can
now
hear you.
stable. Okay. Okay. Fortunately, I'm back. Perfect. You just slide to your first slide one. We gonna make that one.
Am I on the first slide or not yet? So can you see the first slide?
But if there is some.
I have the first slide shared. I don't know if you can see it or not.
Okay. Okay, no problem. Yes, now I can see it. So I can count down from 3 to 10. I will make the screenshot. Yeah. 3, 2, 1. So now let's wrap up this session. I thank you all. I appreciate your attendance. Please feel free to, and do not forget to reserve your calendar for the 16th. In case you will have some comments or question, you can ask via us or you can just contact him directly. He's so kind to be in touch with you for sure. Yeah, so, okay, good. So, wish you all the best and we will be in touch. Have a nice day, everybody.
I'm gratified, and I wish everybody good health and welcome in your career whatsoever. Have a good day. Bye.
Perfect. Thank you so much, Abba. Thank you so much for your time and for the presentation and addressing the comments. Perfect. Thank you so much.
No problem. Have a good day. Bye.
Thank you. I appreciate it. Have a good day. Bye-bye.
Bye.